Welcome, yes, to ECE 320-001, Section 1 of 320A. There is only one section, so you don't need to fill in that square necessarily on the sign-in sheet if you do not want to. We do not have any other sections this semester. A few of you have already been studious enough to know that there's an assignment. You've completed it, but for the rest of you, there's a passport assignment, and that's due Sunday evening at 11:59. Next Tuesday, I won't allow you into the class unless I have your passport. It's kind of one of those TSA things, if you've been. Not really. Today, I want to, I'm Hal Tharp. If you were expecting Dr. Bose, then you were expecting 340, which is in another building. We did a flip because we had a few more students than 340 has, and this classroom accommodated the overflow that we were going to experience if we were in that classroom. Thank you for paying attention to your news feed on D2l or the various emails that we've been trying to send out. I am recording the lectures, and hopefully that means that you might have access to what I'm writing on the board and what I'm recording with the audio. But who knows, if we have technical issues, it's best that you're here in class trying to follow what's being done. But sometimes that's easier said than done for you in terms of attendance, but you will have the ability to go back and review material if you want to, or fill in your notes if that helps you. Attendance sheets are being passed around. I think we've already gone over that. The other goals that we want to with the preliminaries are go through or just briefly discuss the passport assignment and talk about the syllabus. The one thing that you will want to be clear on is we will be using mastering again like you did in 220, and this is not meth ARP, it's ME THARP. So it's Mastering Engineering THARP, my last name, with some numbers after it, so don't get hung up on the METH, but that does start the course ID. You'll need that in order to sign up for this class. And there is already an assignment, but it's basically to familiarize yourself with mastering engineering. You can quickly go through that if you already feel comfortable. It's not graded, but if you want to refamiliarize yourself with that, you can, and I'll try to get homework assignment 1 up there rather quickly. And then the other 2 goals for today, we'll have a quiz. Work out some of those kinks from the summer, and then we will provide, that will lead us into an overview of the course. Let's now talk about the 2. Here's your passport in. Your name, a nickname if you don't go by your official name. If you like to be called Sam, and your first name is Robert, and I won't have any way of knowing that, so your nickname would be Sam. A photograph, make sure it's up to date, so I don't have to do the milk carton age progression. If you have a kindergarten picture or a first grade picture, that may not help me much. But put something in there that's a little more current that I can then tell who is who. Something that's interesting about you, not that you're, I'm the tall, skinny guy in the back. That I may have a lot of those. So give me something that maybe you enjoy cooking certain kinds of food. That may be a little bit different for an engineer, but maybe not. Maybe half of the class enjoys doing that, as do I, if I have time, if I'm not grading. So if you have food on your papers when they're returned, I apologize. I usually ingest most of the food, but sometimes I get a little sloppy. Then there's two more parts to the passport. One is a learning styles quiz that you can link to, and then I want you to actually provide that resulting data in two forms. One will be to simply follow this example, and if you ended up being a more active learner with maybe a score of 2, then you would underline active, get rid of the reflective underline, and put a 2 there, for example. I also would like for you to fill out the D2l quiz. You'll go to the quiz tab on D2l and answer the 8 questions. Oh, were you active? No. So there's a not applicable, an NA button, radio button that you can click on. I was reflective with a score of 3. Okay, the next question will tell me that I was reflective, and now I need to just hit the radio button for 3. That is the learning style quiz, and I'm trying to have you just understand that there are different ways of processing information, and we all learn differently, and it's not like one style is preferred over another. It's just a way to make you more aware of the different ways that we take in information, and hopefully it's designed to help you figure out what works best for you. Then I found that some students like to read these 10 rules. There's 2 sets. There's a good set and a bad set from Barbara Oakley. The link will take you to these single-page studying guides, and I want you to then reflect on the good studying habits and the bad studying habits and write a couple of sentences relative to each one. That's the passport assignment. The syllabus. The main thing is you found this classroom, and the other part of this syllabus that I want to cover maybe today concerns the breakdown of what you will be graded on this semester. We will have several midterms, 3 to be more precise. They will be each worth 20% of your grade. The homework, again, that's on mastering, it will be 10%, and I'll try to set that up so that you have unlimited chances to answer. So you're not going to be deducted if you, oh, I put in the wrong units and now I lost. It'll coach you maybe, and sometimes that coaching may be better than at other times. I think you've probably learned that from 220, and I don't want you to be penalized for that. Okay? And just a hint, sometimes the homework might be multiple choice, and you have an unlimited opportunity. It might not be hard to ace that particular question, just saying. Okay? Then here are some quick outcomes that represent essentially the last half of the textbook that you already have, I hope, in your possession. And then the last page of the syllabus outlines it a little bit more, in a little bit more detail as far as what we're going to do. We'll be starting in chapter 10, which means that we are picking up with sinusoidal steady-state material from chapter 9, and now we're going to start with power and work our way through that remaining half of the textbook. Let's then, are there any questions? I'm going to be holding office hours. That might be another important aspect of the syllabus. It's about the 4th line down. Hopefully I will remember when those occur. They're staggered, but it looks like it's the last half of the week. There's a couple of hours on Wednesday, and 1 hour on Thursday, and 1 hour on Friday, and I haven't yet decided when I will make the homework problems due, but it may be on the weekends. Friday night, they start upgrading D2l, so maybe I won't have it done or due on Friday night at 11:59, because that's right in their window of when they say we are maybe changing D2l. I don't want the technology to hinder your ability to do whatever it is that we're working on. But I guess it won't matter if you're not submitting it necessarily if you're doing it on mastering. So maybe I will make it. Maybe I'll do a quiz tomorrow or Thursday and see what dates you would prefer. Friday, Saturday, Sunday. None of the above. Is that what? Be thinking maybe about that. I don't know if I will give you a chance to decide or not. Here's your quiz. I want you to find the time domain answer for the voltage dropped across the load, which is made up of two elements, a resistor and an inductor. And we also have a couple more inductors and resistors. And the source over here on the left is a cosine waveform. I want you now to find if this is the source, so if you don't feel comfortable with this, redraw it, and maybe now you would say, I need to have it looking like this, then that's what you have. There's your source. The source is a cosine waveform. That yellow doesn't come through very well, does it? But I didn't want it to cover up everything. That's now being applied to this circuit, and I want you to come up with that wasn't sinusoidal, was it? That was sort of a ramp. Sorry, if you're not in the classroom, you're wondering where that signal came from, but this is a sinusoid. Let me give you a few minutes to do that. Did everyone see the percentage of your grade on the in-class material in the syllabus? That was 98% of your grade was the in-class quiz material. Hand in your papers. No. But is your adrenaline flowing a little bit more than it was? What if this was presented to you in a job interview and they said, come on, aren't you an electrical and computer engineer? Where did you go to school? And then you say University of Arizona, and they go, uh-oh, who did you have for circuits? Oh, no wonder. So I don't want that to happen. But if you're in a job interview and they give you this, what's one way? Let's say you don't even really have an idea how you want to begin. Let's sort of talk our way through that. And that's really what the person probably in the interview would like to see, that you can think your way through a problem. So let's say that we don't know where to start. And I won't ask for a show of hands as far as how many people fall into that category. But that's okay. We're coming back from summer. What we want to do is start to think our way through this and get a feel for what's going on in circuits. One way to start any problem is maybe that you are uncomfortable with is there any way to simplify this? Is there some way to simplify the problem? If somebody asks you to simplify that problem, what would you like to change? So now get rid of the inductors, huh? And in getting rid of those, the way that you're getting rid of those is not opening them up, you're shorting them out. You're replacing those inductors with a wire. So instead of that being some energy storage element, what if I just replace those inductors with a wire? I just want to give him an answer or her an answer. I need to kind of get started. So what if we neglect the inductors? And by neglecting, I'm not opening up, because if I open up, what's V sub L if I open up the inductors? Nothing. Well, it's going to be a mess, isn't it? If you had that inductor up above replaced with a short, then you simply would be measuring the source voltage. But let's now neglect the inductors in the form of replacing those with just a wire. So that now, what do we have? Now we have this source. We have a line resistor of 2 ohms. And we have what we started with in terms of our load resistance of 78. And now this isn't quite what I asked for, so I'll give it a hat. It's not quite what we were looking to find. But now, do you feel a little bit better as far as solving that problem? What? Most of your voltage at the source is getting placed on the load resistor, isn't it? There's not a whole lot of voltage drop in that line. So if you wanted to, if this was the case, you could say, oh, in this case, the load voltage is approximately the source voltage, because this 78 is so much bigger than 2. And I could even make it easier. I could just replace that 2 with a short. And now what do I have? I basically have the load voltage is the source voltage. But if I don't do it that much in terms of simplification, you could solve this one, I hope. And what's a quick way to think about solving that? Voltage divider. And if that didn't immediately come to mind, you could say, well, I can find the current flowing in that circuit because I can determine the total resistance across that source. So you could say, or I'm going to find I of t. And once you have I of t, then I hope that you remember, and this is something that you remember until you retire, one of those facts that you have to just know, Ohm's law. That you better remember until you retire, right? What's Ohm's law? V is equal to IR, or however you want to remember it, okay? But if you know I sub L, then you know that this V sub L hat is just R sub L I of T. And I of T was just the source divided by the resistance. And if you wanted to now explain what's going on to the person asking you the question, you might say, what was V sub S? Let me make that red. So here is, and that's supposed to be a sinusoid. The period wasn't supposed to change, it was fixed. This is now V sub S. What's V sub L hat look like? It's a little smaller, isn't it? But how is it aligned with V sub S? It's the same, isn't it? This is a pure resistive network, and so we don't have any lag or delay between our input and the output. And that means that all of the signals in that circuit are aligned. So I'm going to be shaking things in this class. We're shaking this circuit at 60 hertz. And because it was a pure resistive circuit, everything in that circuit is shaking at the same frequency. And if we now had to draw, and this will be a test of my sketching, but it's going to look, oh boy. But you get the idea. It's a little bit less. It's supposed to be the same shape. And there's V sub L. And that might get you to the next interview, maybe, just making that thought process evident to your interviewer. Oh, I kind of like the way that person thought about the problem that I gave them. Now you say, may I go get a drink, please? That's okay. You can kind of get your way or get out of that problem. That's a good way to start solving problems. And now you come back refreshed and you go, oh, now I kind of remember. That was a sinusoidal source. Let's see, Marcelin, chapter 9, sinusoidal steady state, right? And if you have now a sinusoidal steady state problem, what's one of the main parts of that problem? Or what's one of the main ideas in sinusoidal steady state? You're shaking, aren't you? You're hitting something with a particular frequency. You need to know, what is my omega? And omega is 2 pi f. And in the example that I presented, f was 60 hertz. So it might have been coming out of the wall in the United States. Some other countries might have 50 hertz for their source or for their power distribution. This now roughly in omega is 377 radians per second. And once we have that, now we can say, oh, now we're in this analysis mode of sinusoidal steady state. And we are engineers, electrical and computer engineers, and we like to go or think in many different ways. One is in the time domain, another is in the frequency domain. And if we're doing sinusoidal steady state, if we don't really want to be messing with differential equations, you could write a differential equation to govern the dynamic behavior of that circuit, but what were you probably thinking of? Oh, I really liked doing this analysis. Could I do something like that again and simply call this maybe Z1 and this is Z2, and inside those I'm going to put the series inductors that we had before. And now I can do the same thought process, but I'm doing it with sinusoidal steady state, which means that now, instead of time domain differential equations, I can start playing with complex numbers and just doing algebra. That was the whole point of being able to transition these time domain sinusoids into amplitude and angle. And these different circuit elements I can now represent as impedances. For example, what's the impedance of the load inductor? Do you remember what the impedance Z was for an inductor? J omega L when we're doing sinusoidal steady state. Eventually, when we get into Laplace, that will just be SL. It will be even easier, but S will be a more general form of this impedance. But for now, sinusoidal steady state, that J is the square root of -1. Omega L, in our case, J. Omega we just found was 377, and the L, I hope this is what I had before, was 156 millihenries. And if you do the math, this becomes J 59. And that's two of the pair, or that's paired in the Mastering Engineering course ID, if you're just paying attention, right? That was ME Tharp 59 159. I designed this lecture just for that purpose. Coincidence. If that's the case, what's the line? So that's Z sub capital L. Z sub little l, again, is J omega L. Maybe I should say that's L and this is little l to distinguish between those inductors. This is now J 377, and here it was a little bit smaller inductance. And capital Z sub little l is J1, and that's the other number in Mastering Engineering ID. Who knows what you're going to find out in this class? Making all sorts of connections. That's what you want to be able to do. What's the impedance of the line resistance? Is it a function of frequency? No, these resistors are independent of frequency. That was just equal to R sub L, which is 2. Z sub R sub capital L was R sub capital L, which was 78. And if our source, V sub S of t, is now this 311.1 cosine of omega t, where omega was 377t. If I want to write that in terms of a phasor, and I may be consistent, I may not with the notation, but hopefully by context you'll know what I'm talking about. I can't bold things necessarily in these notes, but I can put a bar over them. Now this is a complex number, it's a phasor. What are the pieces of that phasor? And this is a really hard question, but I'm trying to get us back to at least walking with a brisk pace by the end of the lecture so that we're ready to go for chapter 10. on Thursday? What's a way of describing the phasor form of that time domain waveform? What are you extracting from that time domain cosine waveform? The magnitude and its phase or angle. What's the angle of that argument in cosine? 0. And the magnitude? And that's now in volts. Now, what can really hang you up is we can play with phasors and adjust that magnitude to different values. In this case, this is the peak voltage or the maximum voltage of that sinusoid. You could also, and we will probably in chapter 10, when we're dealing with power, we'll probably want to be playing a lot with RMS values. If we now have a sinusoidal waveform and we want the RMS, how do we convert that maximum magnitude into an RMS magnitude? And this is as long as it's a sinusoid. It's just a scalar change, isn't it? And that scalar is this factor of the square root of 2. So I could now say, oh, V sub S RMS, still as a phasor, is V sub S max over the square root of 2. I'm not changing the angle at all, and the reason why I started with that 311.1 is when you divide by 1.414, it now becomes 220 volts. And that's now in RMS units. And that might be more convenient for our problem solving as we work through chapter 10. Now we can actually redraw that circuit in maybe a cleaner way. We now have this was, remind me, was it 59? This was 78. This was J1, and this was 2. And now this, let me not even label it. This source was now 220 at 0 degrees, and we now need to find this phasor load voltage. Is that clear where that came from? How did we transition from the original problem into this? You need to be comfortable with that process. We needed to find omega. We needed to convert these inductors into their equivalent impedance values. And now, if you wanted to, you could say, I would like to know this current, which I could label as a phasor. And I know that what? If I know I sub L, or I'm sorry, I sub T bar, then I can find V sub L bar as 78 plus J 59 times I sub L, I sub T bar. Are we comfortable with that? Yes, question. So why did we do the root mean square voltage, or why did we convert the supply from a maximum phasor representation to an RMS phasor representation? At this point, we wouldn't have to. We did it just to get us ready for all of these power formulas. It will allow us to essentially get rid of factors of 1/2 in our formulas. And we can think of power as V times I or something like that without factors involved, as long as V and I are in RMS values. So for now, we really didn't need to, is the short answer for why did you convert from a peak phasor to an RMS phasor. It's just a scalar away. And if you need to now go back into the time domain and give the actual time domain output expression, you would have to upscale that by square root of 2 to get the maximum peak correct in your answer. Yes? So how does the RMS help us? It won't help us necessarily today in this discussion. It will become, I hope, a little bit more clear when we get into the power formulas. Right now we are in the frequency domain in the form of phasors, and we can now either have that phasor magnitude in an RMS unit or in a maximum or peak unit. And I just want you to be aware that that might be having either peak units or RMS units. And I think I've made you aware of that. Whether you need them or not is another thing. Okay? Now, how do we find the phasor current, I sub t? Can you do that? If I gave you a napkin and a marker, could you, on that napkin, find I sub t, or at least an expression for I sub t? Maybe in this interview you don't have your best calculator in your breast pocket of your blazer. Maybe that's a good thing. So now you say, do you have some paper that I could work on? Yes. Yes, this is basically a KVL problem, isn't it? A Kirchhoff's voltage law in complex math. Meaning we can sum those impedances, and they've been designed to sum nicely. 2 and 78, 80. 59 and 1, 60. We have an 80-60 complex number. We're going 80 horizontal, 60 up. And we can find the hypotenuse of a right triangle to give us the magnitude. We can find the angle of that right triangle with some trig. Meaning, we can now find I sub t. Again, we're now using RMS, which is fine. And we have 2 plus J1 plus 78 plus J59. You just told me that that sum is 80 plus J60. That's maybe denoted by capital Z sub t. And if you wanted to, you could say, oh, here's 20, 40, 60, 80, 20, 40, 60. Now I'm going over 80 horizontally. Here's my real axis. Here's my imaginary axis. The hypotenuse is the magnitude of that complex number. Here's 80. Here's J60. This angle is theta. And I could now write Z sub t in terms of polar notation. It's now the hypotenuse and the angle. Vertical distance is 60. Horizontal distance is 80, and I can do the inverse tangent to find that angle. And if you've drawn your real and imaginary components to scale, you can eyeball what that angle is without needing a $200 calculator. You can get a good feel for that. You know it's what? Less than 45. That may be all you need to know. There's the solution. Did I get 100% on that as a class? Maybe not in the 3 minutes that I allotted, but that's where I want you to start coming back from the summer break so that you're ready to go in chapter 10. Now we are going to proceed in this class with power. That's chapter 10, and we need to know sinusoidal steady state. What's power? We have all sorts of different ways of describing power. If we wanted the instantaneous power, you now have V of t and I of t as a function of time from our analysis that we just performed, and you could multiply those out. And then you would have this expression for power as a function of time. Sometimes we don't need to keep track of power in that much detail. We want to know maybe what is the average power? Or we will learn that that's the same as the real power. And we are going to give each of these powers different units, so that if I label something with a unit, that now gives you a clue as to what power I'm talking about. If you paid your power bills this summer, what were the units that you maybe saw on your power bill? Kilowatts. What were you paying for? Kilowatt hours, energy. Right? You were consuming some amount of energy. And what's a home? What's a typical home's power demand? Anybody have a guess? Maybe it's not fair to ask that question in a desert city like Tucson on a hot summer day. But on average, what's a way of thinking about an average home in terms of its average power 24/7? How much does it consume? How many? 10,000. I hope not, but we being, yes. So you might be an electrical and computer engineer and have all sorts of fun gadgets. You might be in your man cave and drawing 10 times what is normal. Normal is about 1 kilowatt or 1,000 watts. That's a normal home, day in, day out. Obviously, it fluctuates, but that's sort of the nominal. And that's basically just a hairdryer, isn't it? Well, you guys don't use hairdryers anymore, do you? Well, what's a hairdryer? But they used to have wattages of about 1,000 watts for a hairdryer. But taken on average, a home is consuming 1 kilowatt or 1,000 watts, and that's the real or average power. As you start moving up into higher and higher levels of power, these motors and machines start playing a role. And they are not just pure resistors. There's a lot of wire in some of these loads that the power company is having to supply in these big factories, potentially. And those now are looking more like maybe inductors. And we are a little bit off in terms of our time or lag between the input and the output. And we might need to keep, well, we do need to keep track of it. The power company does. You, as a home, you look pretty much resistive. Your loads aren't that heavy duty. But when you get into factories, Now we actually have reactive power. And now we have real power and reactive power, a real part and an imaginary part. We have complex power. Not just complex meaning complicated, but complex meaning a real part and an imaginary part. And the imaginary piece keeps track of the inductors and the capacitors that are attached to our system. And big machines, big motors look inductive, or they have inductive pieces to them. And we use different units for the reactive component, and that's volt amperes. That's the power of everything, volts times amps. Volt amperes reactive. That's where VARs is coming from. If you hear me say VARs, that's the reactive component of the power. The combination of those two gives us complex power, and that will just be volt amperes. And complex is both the real part and the imaginary part. If we just wanted to know the magnitude, that would be what we call the apparent power. And it too has units of volt amperes. All of this stuff, I think, is new to you. That's this course. That's chapter 10. We need to learn how to keep track of all of the powers. Real, reactive, and complex. Then we will up that a little bit, and we'll introduce three-phase power. This is all happening with everything in phase. We have one phase, single phase. That's what you're used to in your home, typically. But as you increase the power flow or demand, it becomes maybe more effective, more efficient to go to three-phase systems. And now everything, each of these phases, we have an A phase. We got very creative in naming these phases. We have an A phase, a B phase, and a C phase. A, B, C. So we'll be saying our ABCs either in a positive way, ABC, or in a negative way, ACB. We'll have different phase sequences. Positive phase sequence, negative phase sequence. And all of these then will help us step into a power problem that might be more industrial than what you might have in a home or residential environment. And we need to learn that. And we're now moving big blocks of power around with three-phase power. That's chapter 11. Then we want to step it up a notch and do more than just sinusoidal steady state. We want to start playing with transient behavior and not having to necessarily worry so much about differential equations, but solving these algebraically with S's, or the Laplace transform, meaning we will generalize from sinusoidal steady state and that's going to give us then another frequency domain to work in, the Laplace transform. And have you all seen Laplace transforms? Somewhere, maybe, in your differential equations class, maybe. These are going to allow us to not only worry about sinusoidal steady state, but also to at the same time handle transient behavior. So we'll have transient, we'll have steady state, or I might call that the forced response. And we will be able to, with the Laplace transform, take care of a lot of different ways of formulating the problem, and one of those is maybe we want to know how do we incorporate initial conditions. Maybe the initial current flowing in an inductor or the initial electric field on a capacitor. The energy stored in these devices, we want to now be able to incorporate into our solutions. The other thing that is nice about moving from differential equations into a Laplace setting is now we can open up the box and be looking at more than just RLCs, second order circuits. We can have much higher order circuits, or we can have more than just one or two energy storage elements. And what do I mean by energy storage elements? Is it clear what I'm meaning by that phrase? When I say energy storage elements, what are you going to be thinking in this class? L's and C's. Oh, and you might wonder, why is he using script S's? Those are maybe easier than my S's and 5's might look too similar, and so you might go, is that a Laplace variable S? Is it a 5? What's he drawing? What's he labeling? That's why I use scripts for my S. That's where that's coming from. Okay? So that you're not confused whether that's an S or a 5. Once we have, let's say, a circuit, and this might be on your first exam, maybe we have 10 energy storage devices, 6 inductors and 4 capacitors. And I have drop forms available here as you're leaving the room, if you need to sign that after today's class. But it shouldn't really be that big of a deal. You can now formulate the problem, and maybe I want to know what's the voltage at this location in the circuit relative to this input. We want to know what's the transfer function between the input and the output. And this Laplace transform terminology and way of thinking will allow that to happen. We can now, with more energy storage devices, start playing with transfer functions. And once we have transfer functions, now we've basically collapsed or aggregated this complicated circuit with maybe 10 energy storage devices into one transfer function, which is a ratio of polynomials in S. So that now we have our input, capital V sub I of S. That's the Laplace transform of our input waveform, V sub I of t. We have our transfer function, H of S. And that now represents our system. And once we know that, now we can compute essentially with algebra in the frequency domain. We can now take this system and represent it like a block, apply an input, and multiply the transfer function times the transform of the input waveform to produce the Laplace transform of the output. Maybe it's not so immediately clear what the Laplace transform of this input signal is, but we can find the transfer function. Well, you're going to learn tools that will allow you to analyze those systems. For example, maybe you want to know what is little h of t. That's the inverse Laplace transform of capital H of S. terminology. Little h of t is the impulse response. And that will come in handy when we want to find the output due to a very generic input waveform to have access to the impulse response. We will also learn how to talk about how do we convert this transfer function into something that might help us analyze circuits in the frequency domain like we started class with, in terms of what can we do in terms of sinusoidal steady-state behavior. Well, we can simply change that S, which is the entire complex plane, to look at just what's happening on the imaginary axis. And that will now give us h of j omega, which we will term the frequency response. And I'm guessing that you've already seen some of those in your home. Maybe not next to the electric chair, maybe closer to your television or your audio system. You have frequency response staring you. Does anybody have a graphic equalizer anymore? What are you talking about? Or do you have a volume control? Maybe do you have a bass and a treble? Maybe. That's adjusting the way your system responds to certain frequencies. That's like you're changing the frequency response of your amplifier. That's what this would be telling us. This is how that system changes the way it behaves to certain sinusoids. If you shake it at one frequency, it might behave differently if you shake it at another. And this tells you, this h of j omega tells you how its magnitude and angle change as a function of frequency. How does it attenuate the amplitude as a function of frequency? We will learn how to sketch this by means of a picture. And I think when you're looking at your learning styles, most of us as engineers are very visual learners. We like to see pictures. Granted, my pictures aren't as nice as what you can do, but there's a picture. That conveys a lot of information. If I had to write that in a paragraph, it wouldn't be clear, would it? As clear. I could try to make it as clear as possible, but we are very visual. We will learn how to write this or represent this frequency response as a picture. Have you ever heard of Bode plots? Maybe not. This is magnitude as a function of frequency. This is angle or phase as a function of frequency. That we need to learn how to do. That's in your appendix of the textbook. How to sketch those by hand. You can have MATLAB do this all day, but you need to understand how that MATLAB was produced so that you have a better feel. Or if you want to start designing filters, you may have a particular, maybe this is now the way that h of j omega magnitude in, let's say, dB looks, where this is now omega. What kind of a filter is that? Low pass. It's favoring the low frequencies, it's passing the low pass, or the low frequencies, and it's attenuating the high frequencies. That's a low pass filter's magnitude response. That's a frequency response. We can also go back and we can say, wait a minute, what can we do with h of t? Remember what that was called? You can look back. Yes, that was the impulse response. I'm going to have another quiz, aren't I? Since it's 98% of your grade. I don't forget some numbers. Hopefully you hope I forget others. That's the impulse response. What if somebody gave you a generic v sub I of t, meaning something that might not have a very easy waveform to take the Laplace transform of, or to find the Laplace transform? You can combine these. You can say, oh, this is my input, v sub I, being adjusted or modified by the system's impulse response. How do you do that to produce an output? What's the key word here? If you have an input processed with an impulse response in the time domain, what kind of an operation are you actually doing? Trying to give you some hints. I was going to let Vanna maybe supply you with some vowels. And yeah. Convolution. We will learn how to perform convolution. And we have even a way of writing that. The output voltage, or the output response, not only will it be written as a convolution integral, but we might use the shorthand of saying that's not a multiplication symbol. That is, in fact, the symbol that we will use for convolution. So you now need to convolve this generic input with the impulse response to produce the waveform of the output. Meaning, if somebody gave you, maybe this was the v sub I, a pulse, and they applied it to a system that had as its impulse response and that shouldn't have really gone to 0, but it will realistically die down. What's the output going to look like? Is it going to look a lot like the input? Will it look not much like the input? That's what you're going to learn in terms of this concept of convolution. If h of t, if I said, can you tell me what the impulse function looks like, would you know what I was talking about? Do you remember what a step function is? 1 for all time, starting at 0. What's the impulse function? Do you remember? Impulse function, not the impulse response. But if I hit a system with an impulse, what's going to happen? What is an impulse? It's an infinitely tall amplitude, isn't it? Over an infinitesimally small time window. That's an impulse. You've heard of that. Yes? No? Okay, we will learn that then. So we will hit a system with an impulse, and the result will be our impulse response, how the system behaves. If this h of t looked like an ideal impulse, which now I'm telling you that this would be an ideal impulse. It has infinite amplitude, and it's right at 0, and it's nothing thereafter. What that effectively does is it energizes all of your energy storage elements, all your L's and C's, and then you just get to watch them fade away. That's the impulse response. You energize your system, and then you just let it go. This, let's say, might be what you would see with an RC circuit, the impulse response of an RC circuit. You charge up that capacitor, and then you just let the energy dissipate out. And that's the impulse response. If this impulse response looks more and more like the ideal, then your output will look like your input. This blue line doesn't really look too much like an infinitely tall spike, does it, at 0? Which means then that your output might sort of charge up and then decay, so that we now have this shark fin type of response. That's V sub O of t. But if this blue impulse response was much sharper, then we would charge up more quickly and decay more rapidly. And can you see that it would now look more like that original input pulse? That's what's going to happen, or that's what we will start to learn via convolution. We also want to learn about filters in this class. And we will really have sort of two flavors of filters. We will have passive filters, which means we will just have R's, L's, and C's. Does everybody know that if you went into another interview, this is now your second round, since you were so successful in the first round, and they say, sketch a circuit of a low-pass filter, would you know what to sketch? Could you sketch a circuit of a low-pass filter? An electric circuit. Could you go to the stock room and ask Josie for some pieces and parts so that you could build a low-pass filter? What would you collect in your little basket of goods? And I say, let's just make it a passive low-pass filter, which means I'm not going to have you do any op amps. Those are active. But we will learn how to build active filters also. After today's class, you shouldn't forget this until you retire. There's a low-pass filter, if you haven't already seen that. Here is your output voltage. Here is your input voltage. And we will learn how to select R and C to give us the frequency response that we demand or that we want. We will also not only look at passive low-pass filters or filters, but we will open up another option and deal with active filters, or we will now incorporate into our filter toolbox the ability to use op amps. And now we can build much higher order filters more easily, maybe without having to use heavy inductors. And now maybe we can throw these into space, these filters, instead of, wow, you want an inductor and it costs you how much to get it into space? And inductors are heavy? Maybe not. Maybe we put these active filters in space. And you now know how to do Bode plots. That's maybe the frequency response of this Bode plot or of this active filter, with this being your bandwidth. That's the frequencies that you favor. These on the right-hand side are the frequencies that you try to attenuate or eliminate from your system. We will generalize this filter idea and move into two-port networks. Which just means that maybe instead of thousands of devices we will now collapse all of those. Maybe there's 1,000 devices into here. We just want to know what's the input-output relationship between all of those pieces and parts. And we have two ports. We have an input port and we have an output port. Those are our two ports, and we will look at how to deal with two-port networks. How many have had 351 or are taking 351? It's a prerequisite? Oh, thank you. I was going to say, and I see two hands, and it was a prerequisite for 320. I was starting to question where I was. Yes, so 320 is a prerequisite, and one of the reasons is so that you feel comfortable with these kinds of diagrams. You might then also be talking about H parameters, which are two-port parameters in 351. So you'll see that in electronics. You might also see that in electromagnetics with different kinds of two-port parameters. Then we will, and I'm sure you couldn't wait until we got to the last chapter of this presentation. I'm trying to give you an overview of the semester. You don't know all of this yet. This is where we're headed. But we will also start dealing with general periodic waveforms. Instead of just concentrating on sinusoidal waveforms, maybe now somebody says, oh, here is a waveform that just keeps going and going, and that repeats every t units of time. Here is time. And you now want to know what's going to happen if I apply this generic or general periodic waveform to a circuit. What's the circuit going to do? I've learned how to do sinusoidal steady-state analysis. I know how to do convolution if I have a particular input waveform. Now I want to know, how do I analyze a circuit's output if I apply as an input this general periodic waveform? That doesn't look sinusoidal, does it? But what do we do as engineers? We try to make them look like what we're comfortable working with. So we will now represent this periodic waveform as a collection of sine waves. And what's that called, that process? Fourier series. Now we will represent this V sub I of t, a generic periodic waveform, as a infinite sum of sines and cosines. Where this omega naught is 2 pi f naught, which is 2 pi over t. So we will learn, if you can now identify the period of that general waveform, which is what's the minimum length where this waveform begins to repeat, that's the period. Once you have the period, now you have the fundamental frequency of that waveform. You have its omega naught, that's 2 pi over t. Then you can start to find these coefficients, a sub n and b sub n. And once you have that, now we're back on firm ground in Chapter 9 doing sinusoidal steady-state analysis. We'll just use superposition to figure out how does a sub 1 get changed as it passes through this system. How does a sub 2 get changed? We'll just superimpose all of those answers to end up with our result. That's where we're headed. We'll start there by baby steps in Chapter 10. I'll see you Thursday.